Welcome to the video for Chapter 14. Today we're going to discuss magnetic materials and magnetic circuits. It turns out that all solid materials and also all liquid materials, they react to magnetic fields, but they react in three different ways. And so we're going to talk about diamagnetism, paramagnetism, and ferromagnetism today. The first two of those are really very weak effects, and we're going to see that it's really ferromagnetic materials that are going to be by far the most important, as we've already discussed briefly so far. We're going to calculate the magnetic field intensity, that will be the variable H. So we're introducing a new variable to represent magnetic fields, just as we had two variables, E and D, to represent electric fields, so we will also have two variables, B and H, to represent magnetic fields. And then we're also going to explain hysteresis, and we're going to discuss magnetic circuits. What is a magnetic circuit, and how can we analyze a magnetic circuit? Our historical perspective today is one of my favorites. Oliver Heaviside, you can see from his picture that he's actually quite slim. He was a self-taught electrical engineer, physicist, and mathematician. And the most important word in this whole description here is self-taught, because he was not part of the establishment. He was kind of an outsider, and he was always putting these ideas into the discussion that the insiders didn't like. And so I really, sort of along with Nikola Tesla, I really like Oliver Heaviside. And if you have the opportunity to study his life more, I would encourage you to do that. Just know that a lot of the words that we use, like admittance and conductance and impedance and inductance and permeability and permittivity and reluctance, two of which we're going to see today, permeability and reluctance, he coined those words because he was the first person to do work in those areas. Okay, briefly, there are three types of materials. There are paramagnetic, diamagnetic, and ferromagnetic. There are a couple of other very special cases, but by and large, these are the most important. Diamagnetism is quantum mechanical. It really refers to electron orbitals that slightly shift in response to an externally applied magnetic field. So if you have, and this is a simplification, please understand it's a simplification, but if the electrons were going in a circle around the nucleus, and you applied an external magnetic field, then that circle would perhaps shift to become a bit more of an oval. And I've exaggerated the effect here. It's actually quite a very minor effect, but that shifting in the electron orbitals actually causes the electrons to shift in such a way that the magnetic fields will be repelled from the material. So that, and here's a completely different picture, if I have a piece of diamagnetic material here, and I try to send magnetic field lines through it, well then rather than actually passing through it, some of the magnetic field lines are actually going to be pushed out of the material. And so it's not a strong effect unless you're talking about superconductors, in which case superconductors are perfect diamagnets. They actually completely repel magnetic fields. But for most materials that we're talking about here, things like water and bismuth, mercury, silver, a lot of metals, we're going to find that those are going to be weakly diamagnetic. Paramagnetic material, and I should just clarify again, all materials really are diamagnetic at their heart. All materials exhibit diamagnetism. It's just that the other two effects we're about to talk about will outweigh those effects and cause them to be hidden. Paramagnetic materials are weakly attracted to externally applied magnetic fields. And the reason for this is that they have unpaired valence electrons. And again, this is not a class in quantum mechanics. As much as I wish it were a class in quantum mechanics, it's not. We're not talking about atomic physics here, but just know that we have two electrons in each orbital, one that's spin up and one that's spin down. That's a bit of a misnomer. The electrons don't actually spin, but they do have a magnetic field, and the spin up electrons have a magnetic field that is in the opposite direction to the spin down electrons. So if the orbital contains two electrons, then those two magnetic fields will perfectly cancel. But if the orbital only contains one electron, there's nothing there to cancel it. And in that case, then it would respond to an external field by distorting the orbital shape even more strongly, but in the opposite direction. And that causes the atom to align with the magnetic field. And common paramagnetic materials include oxygen, aluminum, and titanium. These are weakly attracted to magnets. And so if you had a piece of aluminum, you might think of the aluminum as being unmagnetized, or as being, it would not respond to a magnetic field. But if you had a strong enough magnetic field, you'd be able to detect that there is a weak attraction to the aluminum. But the reason why it feels weak is because ferromagnetic materials are just very strongly attracted to externally applied magnetic fields. Whereas in diamagnetic and paramagnetic materials, the effects are really on an atom-by-atom basis. Here we're talking in ferromagnetic materials about how we have the magnetic domains. The magnetic domains will change in size and shape to respond to an externally applied magnetic field, and that develops an internal magnetic field over long distances. And long distances for us is millimeters or fractions of a millimeter. We can see that there will be an internal magnetic field called the magnetization. And so we're going to talk about magnetization shortly here, but we did see this back in chapter 11, section 11.3. We talked about ferromagnetic materials, and in particular there's iron, nickel, cobalt, and their alloys. Alloys is just a fancy word for mixtures of different types of metal. And so we find that the material is extremely strongly attracted to externally applied magnetic fields. That's why, for example, your kitchen magnets or your refrigerator magnets will stick to an iron or a steel refrigerator, but to a stainless steel, which is actually not ferromagnetic, they won't stick at all. Just to help you understand the relative magnitude of these three effects, if diamagnetism is the weight of a feather, then paramagnetism would be like the weight of a bird, and ferromagnetism would be the weight of a jet airplane. You could imagine how the weight of a single feather wouldn't mean very much to the weight of a bird, and the weight of a bird wouldn't mean anything at all to the weight of a jet airplane. So if you have a ferromagnetic material, you can ignore any other effects. It will just be ferromagnetic. Okay, we've briefly mentioned magnetization, but rather than just doing a qualitative discussion, we need to now have a quantitative description. And so magnetism is going to be represented by the vector capital M, and capital M, as you can see in equation 14.1, is represented by the, and here we have the magnetic dipole moment per unit volume as the volume approaches zero. So it is the infinitesimal volume. How much magnetic dipole moment does it contain? Since we introduced this concept of magnetic dipole moment, now this is the second time that we've used it. We used it originally to calculate the magnetic field due to a loop. Then we used it to calculate the torque on a loop of current going through a magnetic field. And now we're using it to talk about magnetization. So the magnetization M is the magnetic dipole per unit volume. Now, I'm going to flash back to chapter 8 when we first introduced the concept of polarization. Hopefully you'll remember this. If not, you can go back and review it. But you'll remember that we had something similar where an externally applied field caused changes inside the material, and those changes were represented by what we called the polarization field. And we actually discovered that the polarization field was proportional to the electric field. And then we were able to use that to do an analysis that led us to understand that the displacement flux density and the electric field are proportional to each other. And the constant of proportionality, of course, is epsilon 0 times epsilon r. We're going to perform a similar analysis for the effect of magnetization. We're going to see that just as E was expanded to include P, and the combination of E and P represents D, we're going to see that the concept of B is expanded to include M, and the combination of B and M represent H. So we have this new concept of H. H is the magnetic field intensity. The magnetic field intensity, as you can see, includes the effect of the original field that we saw, B, but it also includes the magnetization field as well. Now there's another way of writing this, and that would be that you would have B equals mu sub 0 times H plus M. And this might even be a better way of representing that. The equation 14.2 looks a little bit sketchy in the way that it's written. I like the alternative version even just a little bit more, but in either case you can see that the relationship between H and B is really the same, and how M comes into that effect. Now, we can rewrite Amperes Law. We saw Amperes Law previously, and just as we rewrote Gauss's law to use D instead of E, we're now going to rewrite Amperes Law to use H instead of B. And so you can see the new version of Amperes Law, equation 14.3. This is the line integral of H dot dl equals I enclosed. Now, in the previous version of Amperes Law, there was a mu on the right-hand side, but the mu now appears as part of H in the left-hand side. So the mu is actually now part of the left-hand side rather than the right-hand side. This is an improvement on Amperes Law, and we're now going to refer to it as Amperes circuital law. And we have to be specific about this because there's also an Amperes Force Law that we just recently learned, and so we need to have a special name for the circuital law and for the force law. Sometimes we'll just call it Amperes Law, and if you do refer to it as Amperes Law, it's equation 14.3. We're very close now to this equation being elevated into Maxwell's equations. But there's one last thing that we need to do, and spoiler alert, it's going to happen in 3 more chapters. In chapter 17, we'll make the last tiny little tweak to equation 14.3, and then it will be elevated as one of Maxwell's equations. So you might remember that the strength of the polarization field was proportional to the externally to the externally applied electric field. That was flashing back to our earlier discussion of electric fields. We can make the same assumption here, that the magnetization is proportional to the magnetic field intensity. And so you can see that we're going to have M is equal to chi sub M times H. And that's referred to as the chi sub M is the magnetic susceptibility. Now this is not a perfect assumption because the magnetization field is not exactly proportional to H, but it is true for relatively low intensities of magnetic field. So, often you'll find that there'll be an equation that is true near the origin, but as you get further away from the origin, maybe something else happens. And that's kind of what's happening here, is that within the region of low intensity fields, M is proportional to H. But ultimately, it will not be proportional across the full range of H. Now we can rewrite, if I go back up here to equation 14.2, you can see this is the alternate version that I suggested for equation 14.2. I guess I just should have waited because it appears as equation 14.5. We're now going to take what we know for M, we're going to substitute it into equation 14.5, and we end up with equation 14.6. Now we can factor in H out of each of those two terms in the parentheses. We're left with 1 plus chi sub M, and we're going to define mu sub R to be 1 plus chi sub M. So this 1 plus chi sub M is simply going to become mu sub R. And then as we did with the epsilons, mu sub 0 times mu sub R, we're just going to call that mu. So we have to be very careful. Mu sub 0 is the permeability of free space. Mu sub R is relative permeability of a particular solid material, and mu is the total permeability, which is the product of those two. But the most important thing to take away from this is that B is equal to mu times H. So just as D was proportional to E, we find that B is proportional to H, at least for low field intensities. Here's a table of relative permeability of different materials. These are all ferromagnetic materials because all non-ferromagnetic materials have a relative permeability that's extremely close to 1. It's like 1.0006 or 0.9994. So we're going to really stick around with the ferromagnetic materials. You can see here that there's cobalt, nickel, steel is an alloy of iron. There's a cobalt iron alloy. There's 2 special materials in here called permalloy and supermalloy, and those of course have been the result of hard work by material science people, material scientists, to come up with a way of increasing the relative permeability. And in the case of supermalloy, which has some challenges, we can't use it all the time, but boy, a relative permeability of 1,000,000 is worth a lot of hard work. Notice that there's also 2 entries for iron. There is relatively pure iron, which is commercially available, and then if you want purified iron, I mean that has to be done in a special environment, and this is really more for a laboratory work. If you want to go to the store, go to the iron mill and buy some iron, you're going to get commercial iron, which is going to have a relative permeability of about 5,000, which is still quite good. Okay, thinking back to example 11.6, we talked about the magnetic flux density inside of an air-filled toroidal solenoid. You'll remember that that was the thing that kind of looked like a donut. So we had a donut here, and inside of wrapping around the donut, there were coils of wire, and a magnetic field appeared inside the coils inside the air-filled solenoid. Now, at the time, you might have wondered, hey, how are those wires staying in place? How is it that they're not just collapsing onto each other? And the answer is you wouldn't have an air-filled solenoid. You would have a solenoid that was full of a material. In this case, we're going to fill it with cobalt. Now, in practice, we wouldn't use cobalt, but I'm trying to use a variety of different values here so that you get used to using table 14.1. So we're going to have a magnetic field that's going around this toroidal solenoid, and it's going to have a path of D. And what we found, if it's air-filled, is that B is equal to mu sub 0 Ni divided by D. That was if it's air-filled. But what we're going to do now is we're going to figure out what happens if it's not air. What happens if it is cobalt? So we're going to take the new version of Amperes circuital law. H dot dl is equal to I enclosed. And we can, if we look at this, the magnetic field, there's no reason to think that the magnetic field wouldn't be constant around that entire loop. You know, if it troubles you to say, well, what about the gap in between those? Well, I can add some more. You know, we can have as many of these as we need to. In practice, there would be probably thousands, at least hundreds, if not thousands of turns of this coil. So the magnetic field will be constant. So we can just say that this is going to be H times D. So it's H dot dl, and the integral over dl is going to be the length of that path, which is just d. How many turns of current does it include? It includes n times I, where n is the number of turns of the coil, the number of wires that go around the donut. And so I can solve for this. H equals n times I divided by d, and then I can calculate B. B, I'll say B of cobalt is equal to mu times H of cobalt, and I should probably clarify this is H of cobalt, and therefore this is equal to mu Ni divided by D. So notice really the differences, the only difference between these two equations for air and cobalt is that mu sub 0 is replaced by mu. Remember that mu is equal to mu sub 0 times mu sub r. So we have, let's see, the question was, how much does the flux density increase if the core is filled with cobalt, I should say filled with cobalt, rather than with air? Okay, so how much does it increase? Well, we found out how much the total is, so let's just take the ratio of B cobalt divided by B air, and this is equal to mu sub 0 Ni divided by D divided by mu sub 0 mu sub r Ni divided by D. Cancel the D's, cancel the I's, cancel the N's, cancel the mu sub 0's, and we're left with 1 over 600, and let's see, oh darn it, okay, I did that backwards. So B of the cobalt is mu sub 0 mu sub r Ni divided by D divided by mu sub 0 Ni divided by D for the air. Again, we'll cancel, 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 and we're left with just mu sub r, which is 600. So the flux density increased by a factor of 600 when we filled that core with cobalt rather than with air. You could imagine that if we'd used commercial iron, it would have increased by a factor of 5,000, or different materials, 8,000, 20,000, 200,000, and so forth. So you can really substantially increase the magnetic flux density by increasing or by putting a ferromagnetic material in the core. This is very important to us. We will never have an air-filled core. It will always be filled with some sort of ferromagnetic material because it gives us more bang for the buck. If H equals 100 amps per meter and a solid piece of permalloy, by the way, I forgot to mention amps per meter, those are the units of H of the magnetic field intensity. And a solid piece of permalloy, what are the magnetization field and the magnetization flux density? Okay, so I'm going to go back up here. I'm going to see what is the relative permeability for permalloy, and it looks like it's 8,000. So I'm going to say mu sub r is equal to 8,000. So we know that the magnetization M, and I'm just going to go with magnitudes here, M is equal to chi sub M times H, and we know that chi sub M is mu sub R minus 1. So in this case, that's 7,999. So M then is going to be 7,999 times 100 amps per meter, and therefore I get 799,900 amps per meter. And M, the magnetization field, and H, the magnetic field intensity, have the same units, amps per meter. And so that's one of my answers. And then I can now calculate B. B is equal to mu sub R times mu sub 0 times H, which is 8,000 times 100. Well, I'll say 8,000 times 1.2566 times 10 to the minus 6th, and then that's times 100, and that gives me 1.00 Tesla. And just for comparison, you can also then say that if I come back up here, let's find the equation that I'm looking for. You can also calculate B as mu sub 0 times H plus M. And so if you come back down here, and you can double check your answers, B equals mu sub 0 times H plus M is equal to 1.2566 times 10 to the minus 6th times 100 plus 799,900, and that works out to be 1.00 Tesla. So you can find it in both ways and verify that you got the correct answer. It turns out that, as I mentioned to you earlier, that the idea that the magnetic field intensity is proportional to the magnetic flux density is really only true near the origin. You'll notice that right in this area here, that we can see that there is, in fact, a linear relationship. And if we only stayed within that region, everything would be fine. But as we move further away from that region, let's start out with a perfectly, let's say, a perfectly unmagnetized piece of ferromagnetic material. We're going to start at point A. As we begin to apply a magnetic field, we're going to find that we're eventually going to begin to magnetize most of the material. Most of the domains will have shifted so as to correspond to the magnetic field that's being applied to it, and ultimately there's nothing more that can be done. You know, it's like once every member of your population has been recruited into the army really can't get any bigger, and that's kind of what's happening here. That's why the B is flattening out. Now once that B has been flattened out, if we begin to remove the H, as we remove the H and take the H back down to 0, what we're going to find is that once H is taken back down to 0, those domains didn't all shift back. They kind of stayed where they were. At least some of them did. And at point C, we have now removed the magnetic field, but the magnetic flux density is still there. And that's because some of the domains still point in the same direction. They still remember that they were magnetized. Now, if we put a strong enough negative magnetic field in, we can cause all of those to sort of zero out. At point D now, we've applied a strong enough negative magnetic field to cancel out the memory effect that it had of point B. But if we continue to strengthen and by the way, at this point, we could go back to A. And if we did go back to A, it would be we had just closed the loop. We had gone all the way to B, stayed magnetized at C, unmagnetized at D, and then stayed unmagnetized when we went to A. But that's not very interesting. We're going to continue to make it a stronger negative magnetic field until we have magnetized it all the way the other direction. Then, as we come back, if we stop here where the H field has been removed, then you'll see that at point F we have a memory effect in the opposite direction. We would have to go all the way to point G in order to zero out the magnetic flux density. And then again, we could go back to point A if we wanted to. Or we can continue the loop. We can continue to go from G back up to point B, and we've now closed that loop. So we can return back to point A, but typically what will happen is that the field will be magnetized at point B, then it'll be magnetized at point E, then it'll be magnetized at point B, then it'll be magnetized at point E. And this is a little bit of a hassle. It means that some of the equations that we just derived aren't really relevant, aren't really valid for high magnetic fields. So we got to be careful about that. It's an assumption that we will continue to make for most of this class, but you need to know. Remember, this picture of hysteresis tells us that assumption is not 100% accurate. Although it's a pain in the neck, it can also be our savior, because it turns out all of this text is just saying what I just showed you in that picture. It also means that since material scientists, again, have worked very hard to design materials that have a customized BH curve. So we've essentially said, okay, well, I guess hysteresis is a thing. Let's try to take advantage of that. So if we, and I've sort of left out this initial part here, if we start out at we start out at the origin, we move up to A. If we begin in this new material, if we remove the magnetic field H, gosh, the magnetic flux density hardly dropped at all. And we would actually have to come all the way over here with a negative field to wipe out that magnetic flux density. Then just a little bit more, we're going to go in the opposite direction. And then it'll have a memory effect that it's pointing in the opposite direction. And then it'll be constant for a long range. Notice all of this range here, we're finding that it's always going to be having the negative value. Only then can we zoom up here to F, where we've canceled out the magnetic field, and then all the way back up to A again. If we take this curve, what I want you to think about it as, this is a binary 1. And this is a binary 0. And this is exactly how a magnetic hard drive works. or a floppy disk, or any sort of magnetic memory storage is going to be based on this exact hysteresis curve. And so we can see that having such flat regions on the top and bottom gives us what's called bistability. And anytime that you want a binary system to be stable, you need it to be stable in two states, in the 0 state and in the 1 state. This curve is a perfect example of bistability. Okay, let's finish up today by talking about magnetic circuits. I need to first of all explain why magnetic circuits are a thing. We're going to just briefly mention the energy stored in a magnetic field. You can actually represent this as the integral of H times B. This is exactly the same thing that we saw when we talked about the energy stored in an electric field. If it turns out that our assumption that B and H are proportional to each other is valid, then that equation can be reduced down to this equation. So what I want you to notice here is that the energy that is stored in a magnetic field is inversely proportional to mu sub r. That means that if I have, let's imagine that I have a magnet here. I'm going to choose a horseshoe magnet. And I've got the magnetic field lines are flowing, so this is the North Pole, so they're flowing out of the North Pole and into the South Pole. So as those magnetic fields are flowing there, they're flowing through the air. But often what would happen was that to keep the magnet as strong as possible, they would put a little piece of steel here, or a piece of iron here that they call a tender. So this would tend the magnet. And then the magnetic field lines would flow out of that through the tender and then back down again. This shortcut the path, and it made it so that the magnet could maintain its orientation, could maintain its strength for a longer amount of time. It also meant that if you had an object that was out here, it wouldn't be subject to the magnetic fields because they're all contained within the iron. The reason why the magnetic field stayed inside the piece of iron is because the iron had a relative permeability that was much higher. That meant that the energy would be much lower. So as mu sub r increases, the energy decreases. And so we know that physical systems will always try to strive toward a place where their energy is as low as possible. That's what's happening here. That's why, for example, if you had a permanent magnet, it would stick to a piece of ferromagnetic material. If you had iron filings, they would tend to move toward the magnet because it will always move in a direction of lower energy. And that's also why if you had a magnet, and let's imagine a more extreme case, if you had a magnet that was applied to an external piece of material. So here I'm going to put that horseshoe magnet over here. And you know what? Let me just go ahead and break this middle part here. So I don't have a continuous loop. It's just going to be like a path where it can do this. Well, the magnetic flux lines will actually go all the way through this piece of iron, and then it'll come back here. It'll never jump this gap. Assuming that the gap is sufficiently large enough, it would never jump that gap because it's going to want to be able to stay within the iron as much as possible. So this idea of a magnetic circuit is exactly like an electrical circuit where current is always going to flow through a wire. It's going to flow through a conductor rather than jumping through the air. We don't even think about the fact that the current could conceivably jump through the air. We just say, oh, I see, it's always going to go through that piece of metal. So here's an example of the simplest kind of a magnetic circuit that I can imagine. This is a simple piece of iron or a piece of ferromagnetic material. We're going to have a path length of L. We're going to have a cross-sectional area of A. We're going to have a coil of wire where there's a current N flowing around, a current I flowing around N loops of the coil. And if you put your thumb in the direction of that current, you can see that it's actually going to be pointing clockwise. So the magnetic flux density, the magnetic field intensity, and magnetic flux density are going to point clockwise around this circuit, and there's really no other place where it could go. You know, the magnetic field is not going to go out here and then come back in again. It's going to stay within the piece of material. So we can calculate the magnetic flux beginning with the new version of Amperes circular law. Remember, we had the closed loop integral of H dot dl is equal to the enclosed current. Well, it's H times L is equal to N times I. We can solve that for H. It's Ni divided by L, and we can then use our previous equation to find B. So B equals mu times H. So we just bring in mu sub 0 times mu sub r times Ni divided by L. So the Ni divided by L comes from there, and the mu leads to mu sub 0 times mu sub r. Now we're going to introduce one new quantity called the magnetic flux. Now we've talked a lot about magnetic flux density. We talked about B. Every time I say B, it's magnetic flux density. But it turns out that there is a thing that is used to calculate B. So this is the magnetic flux, and this is the area, and so therefore magnetic flux per unit area gives us magnetic flux density. We could write psi sub m as B times A as well. So if we took our equation from up here, we could write this as B is equal to psi sub m divided by A. And if we just wanted psi sub m, we'd move the A over to the right-hand side, and that's what we've done right here. So psi sub m in this loop is mu sub 0, mu sub r, times n times I times A divided by L. We're going to introduce a new concept called reluctance, and when I write reluctance, I'll use a scripty r. This is the scriptiest r that I could get with my equation editor. So scripty r, reluctance, is equal to L divided by A times mu sub 0 times mu sub r. So we're going to take the A, we're going to take the L, we're going to take the mu sub 0 and the mu sub r. We're going to put those all into a reluctance, leaving only the n times I in the numerator, and that's the version that's shows in equation 14.8. And so notice that we could then rewrite that as psi sub m times reluctance equals n times I. Now, I want you to think about the fact that this n times I, which we're going to call the magnetomotive force, the magnetomotive force is the thing that is causing the magnetic flux to occur. It's the thing that it's the motivational force that is causing the circuit to do anything. The reluctance is the material characteristic that is preventing or is impeding that from flowing, and this is actually the thing that is flowing. So we can say that this is kind of like a current, and this is kind of like a resistance, and this is kind of like a voltage, and if we did that, we would get an equation that looked a lot like Ohm's law. And as a matter of fact, it is perfectly analogous to Ohm's law. We have a magnetomotive force instead of an electromotive force. We have a flux instead of a current, and we have reluctance instead of resistance. But everything else is going to stay the same. So what this means is that we can analyze a magnetic circuit to find the reluctance of each branch, and then from that and the magnetomotive force, we can find the fluxes. And then remember that if you had the flux, you can find the flux density. And heck, if you wanted, you could then use that to calculate H as well. So let's do an example here. What is the magnetic flux density B for the magnetic circuit in figure 14.3 if the cross section is 10 centimeters in each direction, the total path length around the loop is 50 centimeters, and there are 100 turns of wire, each carrying 1 amp. Assume the material is commercial iron. So assuming that we have commercial iron, that means that mu sub r is equal to 5,000. Let's calculate the area. It says the cross section is 10 centimeters in each direction. So that means that it's 10 centimeters in this direction and 10 centimeters in this direction. So the area is 10 centimeters squared. I'm going to use meters, so it's 0.1 meters squared, which is 0.01 square meters. The length is equal to half a meter, because that's 50 centimeters. N times I is equal to 100 times 1, which is 100. We'll call this amp turns. The turns, you could really omit the T. You could just call it 100 amps, but we're going to leave it in there. And then the reluctance is equal to L divided by the area times mu sub 0 times mu sub r. And this is equal to 0.5 meters divided by 0.01 square meters times, and this is a value that we haven't talked about for a while, 1.2566 times 10 to the minus 6th. And that's the value of mu sub 0. And then we have 5,000 because this is commercial iron. And this gives us 7,958. And the units of reluctance are inverse henries. Henries to the minus 1 power. And then from there, we can calculate psi sub m is equal to Ni divided by the reluctance. That's Ohm's law for magnetic circuits. This then is 100 divided by 7,958, and that works out to be 1.26 times 10 to the minus second Webers. Webers are the units of magnetic flux. And then B is equal to psi sub m divided by the area, and we've already calculated the area, so this is 1.26 times 10 to the minus 2 I can say Webers, and then this is 0.01 square meters, and that works out to be 1.26 Tesla. And I don't know if you remembered at the time, but I also said that another unit was Webers per square meter, and we now know why a Tesla is equal to a Weber per square meter, because it is a magnetic flux divided by the surface area. We can also extend our discussion of magnetic circuits to include all of the electric circuit rules that we've seen. Series and parallel, Kirchhoff's laws, mesh and nodal analysis, and so forth. So let's see what happens if we introduce a tiny gap. We're going to say, what is the flux density present in the air gap of this magnetic circuit? You should express your answer in a format similar to equation 14.18. So what did 14.18 look like? It looked like this. So we need something that looks a little bit like that for our answer of what's happening here with this air gap. You might say, really, is there actually an air gap? And the answer is yes, there can actually be an air gap that can be there for a good reason, but as we're about to see, we want that air gap to be as small as possible. So let's see, what would our analogous circuit look like? We're going to need two reluctances now. I'll call this the reluctance of the gap, and I'll just call this reluctance sub 1, because that's going to be the main reluctance of the core. That's N times I, and this would be psi sub m. So we know that psi sub m is equal to Ni divided by, and because those two reluctances are in series, I can call that R sub 1 plus R sub g. And therefore psi sub m is equal to Ni divided by, what's the reluctance of the core? Well, that's going to be L divided by A mu sub 0 mu sub R. And what is the reluctance of the gap? Well, that's L divided by A times mu sub 0, and mu sub R of air is 1. Remember, the air is not a ferromagnetic material. Air is not iron, nickel, cobalt, or an alloy, and so therefore that's just equal to 1. B, then, is equal to psi sub m divided by A, which is Ni divided by L divided by, and the A's are going to cancel, so I'm left with just mu sub 0, mu sub R, plus, oh darn, that shouldn't have been L. The length of that air gap is G, so the gap width is G, so that should have been G. G divided by just mu sub 0. I'll factor a mu sub 0 out of both terms in the denominator of the denominator, and that means that it moves up into the numerator, so this becomes mu sub 0 Ni divided by L over mu sub R plus G. So take a moment and consider that effectively the denominator contains two lengths. One of them is the length of the ferromagnetic material. The other is the length of the gap. But the ferromagnetic material gains the benefit of mu sub R. So the relative permeability shortens the effective length of that material. And since mu sub R can be hundreds or thousands, we can see that length is going to be substantially shortened. In the same way that, if I walked to Wisconsin, if I walked to, let's say I walked to Denver, that would take me forever. But if I flew to Denver, then that would take much less time. And that's sort of what the mu sub R is doing for us there. So let's repeat example 14.3, which was the one with just a solid piece of magnetic material, ferromagnetic material, if we introduce a 2 millimeter air gap somewhere, anywhere along the 50 centimeter loop. And so we're going to find out what happens there. Well, I can just use the equation. It's still up at the very top of the screen there. B is going to be equal to mu sub 0 Ni divided by L over mu sub R plus G. So this is 1.2566 times 10 to the minus 6th multiplied by N multiplied by I divided by, the length was 1/2 meter, divided by, because this is going to be, and it was permalloy, so it was was it permalloy? It was commercial iron, so the relative permeability is 5,000, and then the gap is 2 millimeters, which is 0.002 meters. And if we do all of that, we end up with a strength of only 0.060 Tesla. Well, remember that the strength used to be 1.26. So 0.06 Tesla divided by 1.26 Tesla gives me 4.8%. The magnetic flux density is now 4.8% of what it used to be. that means that it has decreased by 95.2%. Just that tiny 2 millimeter gap has decreased the magnetic flux density by 95%. In the same way, imagine I'm flying to Denver, but halfway through the plane lands in Kansas, and I have to walk 10 miles. Then I get on another plane and fly the rest of the way to Denver. Even though that 10 miles is insignificant compared to the trip to Denver, because I'm so slow in walking that 10 miles, it will substantially change the length of the overall trip. Okay, last example for today. Let's convert the following magnetic circuit into an electrical circuit analog. Write two mesh current equations, one for the magnetic flux in each mesh. Okay, so we're going to have a circuit that's going to look structurally exactly like this one. And if you put your thumb in the direction of I1, you're going to see that inside the material that the magnetic field is going to be pointing upward. So this one is going to tend to be going clockwise. And over here, notice that the current is coming in on the back. So it's kind of hard, but you have to picture yourself putting your thumb in the direction of that current and rolling your fingers way around, and you're going to find that the magnetic field is going counterclockwise in that portion of the loop. So that means that in the center, it's actually going to be adding up, and so they're both going to be going downward. So I'm going to refer to this as reluctance 1, and this is going to be reluctance 2, and this is going to be reluctance 3, and these are going to be both, this is N sub 2, I sub 2, and this is N sub 1, I sub 1. This will be psi sub 1, and this one going this direction is going to be psi sub 2. And I know that I have equations for the reluctance. R1 equals L1 over mu sub 0, mu sub R times the cross-sectional area, and R2 is equal to L2 divided by mu sub 0, mu sub R times the cross-sectional area. Notice, by the way, that L1 is going this path right here. So L1 is just this portion of the path. And then L2 is just this portion of the path. Just this portion here. And then L3 is the middle branch. We could have different cross-sectional areas. We could even have different materials. Even this middle branch could be made of a different material, and the techniques that we're using would work for that. So this is L3 divided by mu sub 0, mu sub R times the cross-sectional area. Now let's go ahead and analyze this electrical analog. I'm going to do by KCl. I'm going to have minus N1 I1 plus psi 1 R1 plus R3 times, and there's actually two fluxes going through there, so that's psi 1 plus psi 3, that's equal to 0. And then also by KCl in the right-hand loop, we're going to have, and I'll go counterclockwise here, so this is minus N2 I2 plus psi 2 R2 plus R3 times psi 1 plus psi 2, and I made a mistake in the previous equation. There is no psi 3, that's just psi 2, and that's equal to 0. I can rewrite these equations in a more standard format. Psi 1 times R1 plus R3 plus psi 2 times R3 is equal to N1 I1, and psi 1 times R3 plus psi 2 times R2 plus R3 is equal to N2 I2. And if we knew the values of R1, R2, and R3, which we could calculate from right here, if we knew those three values, then this would actually, and we knew N1 and I1 and N2 and I2, these would actually be numerical equations, and we could then solve these equations for psi 1 and psi 2, and then we could calculate the current, magnetic flux flowing around the left side, around the right side, and down the middle branch. So summary for today, we have diamagnetic materials, which are weakly repelled by magnetic fields. Paramagnetic materials are weakly attracted to magnetic fields, and ferromagnetic materials are very strongly attracted to ferromagnetic materials are very strongly attracted to, magnetic fields. The magnetic field intensity is defined as a combination of B, the magnetic flux density, and the magnetization. We have a new version of Amperes circuital law, not quite complete yet, but getting closer. We find that for relatively low intensities, magnetization field is proportional to the magnetic field intensity, and that leads us to the fact that the magnetic flux density is proportional to the magnetic field intensity. We also see that ferromagnetic materials exhibit hysteresis, meaning that they have a memory effect. Whenever possible, magnetic fields will always remain in ferromagnetic materials rather than passing through the air. That allows us to study what are called magnetic circuits. Magnetic circuits can be studied as analogs to electrical circuits, meaning that all the tools we've developed for electrical circuits can be applied to the magnetic circuits. And then we can calculate the magnetomotive force, reluctance, and from that we can calculate the magnetic flux, which then allows us to calculate the magnetic flux density if necessary.